In 1887, Michelson and Morley executed a beautifully designed experiment with a huge impact on the development of physics, which went down as one of the most famous experiments in the history of physics, but also as one of the most failed experiments in physics. Well, not really failed, but we'll get to it. And I was captivated by this experiment, and I had to know everything about it. So I spent, I think, close to 300 hours on this video, and I hope that you will enjoy the show. So let's see. Let's dive in. So I made two videos. One is the praise video. This is the praise video. I'm happy. I'm praising Michelson and Morley, and I've divided this video into different parts. Part number one will be to give you some context. What is it all about? Next, we will build intuition in a way I believe can be followed by anyone. This, no matter what your background in physics or mathematics is, it will be easy to follow. We'll do a crash course into light. That's what we need. And then we will be racing a light race and see who wins. We will look at why this experiment is so geniusly designed and executed. We will look at the setup and have animations for them. And we will look at light interference and fringe shifts. We'll get to this, but it's a big part of the experiment. And then we will get to the final conclusion of the experiment. And why do I think this video is different? Because there are many videos on this topic. Well, A, I think I will be building intuition in a way that's easy to follow. B, I will be sticking really close to the actual papers, which is really important to me, not go by a paper on a paper on a paper. No, we will go back to the roots of the experiment. And I will have in-depth animations that go beyond what I've seen online so far. But there will be a rant video, and I will change my clothes into red. And I will rant. I will rant, not about the experiment. I will rant about the way they documented it on paper. They have assumptions just falling out of the sky. There's an error in well, there's actually two papers, the one in 8081 and the one in 8087. And the one in 8081 has an error. Everyone knows about it, has been documented. You can even find it on Wikipedia. It's in there, and we will have a look at it. It does not, however, change the results. It does not change the measurements, and it does not change the conclusions from the experiment. I believe there is a second error in that same paper, and I couldn't find any documentation about it. I know that's a big statement, but we'll see how it goes. I will be adding clarity and rigor to the article. I'm going to say that the graph of the expected results is wrong. Big statement. I will be mapping the numerical results to the graphical results. I could not find any, well, almost no documentation and definitely no videos on how to bring the numerical results to the graphical results. So I filled in those blanks, and then I propose how the final graph should have looked. There's also a lot of mathematics falling from the sky, so I've added all the mathematical steps that were not in the paper itself, and there were some simplifications, and I will deep dive on these simplifications and demonstrate that these simplifications are justified. So why is this video different? Well, I think it's one of a kind. No one is ranting about that. I'm filling in the blanks that everyone skips over. I will be adding clarity and rigor, and as said, I will pinpoint two errors that are not documented. And I went at great length because I know it's a bold statement. Not being a scientist or having a degree in physics, so I talked to an actual professor in physics teaching his students on this experiment in depth. I love those classes. It really filled in some of the blanks for me as well, but the same error is in there as well. So I talked to the professor, and he was kind. He said, "Tom, you're not wrong what you're saying. It's not wrong what you're saying. I have to do some research and go back to the original paper because you're You're absolutely right. So we'll see. But that's for the rant video. Moving on. The actual papers, there's two of them. The one in 1881, which is the thesis of Michelson himself when he was at the US Navy. That's where he designed the first the first experiment. And then there's the second one, which he did with Morley together. And that's the one that got the most fame. So let's open the curtains and see what it is all about. Give you some context, because then you have something to build from, right? So what is it all about? Well, light is a wave. They knew light is a wave. There's this famous experiment, I would say maybe the most famous experiment, I believe, in the history of physics, by Thomas Young, where he demonstrates that light behaves like a wave. It's the double slit experiment. Second, a wave needs to travel through something, like sound waves. They go through matter like air or water or whatever, and they move the water molecules or the air molecules. When you're in the gym and you're doing the ropes, the wave goes through the medium rope. When you look at the sea, the waves go through the medium water, right? So waves, we need medium. Light is a wave, so we need a medium for light. But we don't know what it is really. That's the difficulty, and it has to be everywhere because light can be everywhere. So what is it? And we have to label it. We have to give it a name. And they came up with a word that I can't pronounce. It's the luminiferous ether. I'm going to stick with ether. And the hypothesis of the experiment is that ether, which we cannot explain at this moment, we as planet Earth have to move through this ether at around 30,000. It says kilometers per hour. It should be meters per hour. And if light travels through this medium, then depending on the direction where the light goes to, they will have different velocities. Because if the light is traveling with the ether, it gets a jump start because the ether is already moving. And if it goes against the ether, it's being pulled back by the ether. So that's what's the hypothesis, that if you look at light waves traveling through this medium at different angles, you can figure out if there is ether and that it is that we as Earth are moving around 30,000 meters per second, not kilometers per hour, through this medium. So they did an experiment. They said, well, let's have a race. We have two light waves. One is going against and with the ether, so it's going back and forth, and the other one is perpendicular to the ether. You can visualize it as a wind, right? So you're running against the wind and then with the wind, or you're in an airplane. The airplane has to go against the wind and then come back and has the tailwind and headwind, and the other airplane is going perpendicular to the wind and has some shear. And if you do so, then you will, well, one of them will win. One of those two light rays will win the race, just as it would be for water waves, sound waves, any wave. So they did the experiment, and the result was no. Whatever we do, the light rays will both be exactly at the same time at the finish line of the race, no matter what we do. So we call this a null experiment. Failed. They were failing in demonstrating the hypothesis. Well, it was rejected, the hypothesis. And that made a lot of smart people think, and one of them was Einstein. And well, a few years later, he came with his theory of special relativity. And with that theory, you can perfectly predict why this was a no result. Moving on, now we are going to build context. And the way I'm going to build context is by letting go of ether and light rays. We are going to have a race between swimmers in a river. It's a wild river, and it's moving at 4 meters per second relative to the shore. So here is the river and the shore on both ends. And it's going from right to left 4 meters per second. And we have swimmer A. And swimmer A has the capacity to swim 5 meters per second relative to the water, relative to the river. And that's why I labeled it like the velocity of the swimmer relative, comma, to the river. 5 meters per second. So not relative to the shore, relative to the river. Now I need to make myself small. Can I make myself small? Yep, yes I can. So there's a swimmer B, and he swims also in this river, and he's his twin brother. And they are equally strong, and he can do 5 meters per second as well, relative to the water. But he's swimming the other way. He's swimming to the right. And no, it's not twins, it's triplets. And the third brother also swims 5 meters per second, but he swims up and down the river on a vertical line relative from us as observers on the shore. And now the question is, what is the velocity of swimmer A relative not to the water, not to the river, but relative to the shore? And what is this answer for swimmer B? And what is the answer for swimmer C? And I strongly advise you to pause the video and think about it, because if you are able to do this, you have mastered all the logic in the experiment of Michelson and Morley. All the other stuff will be easy. This is where it happens. This is the magic. This is the difficult part. So really think about it, because I'm going to give the answers right now. So pause it, think about it, and hit play. So number A, even if he's not swimming at all, he's already going 4 meters per second to the left, because the water is taking him 4 meters to the left. But he's adding 5 meters per second on top of it, because, he doesn't care whether the river moves relative to the shore or not. I could blindfold him, close his ears, and he's just swimming 5 meters per second, So you can add those velocities together, and then 5 plus 4 will be 9. And if you do this the same for swimmer B, you will get -1, 4 minus 5 is -1 to the left, is +1 to the right. So the swimmer B goes against the river, 5 meters per second. The river pushes him back 4 meters per second, so net total will be 1 meter per second to the right. The difficult one is number C. It's so difficult that even Michelson himself got this wrong in 1881. It's difficult. I mean, swimmer A and swimmer B is just Galilean relativity, It's just ordinary, everyday Galilean relativity. And if you want to know more about Galilean relativity, of course, I made a video about it. It's at level number 5 on my special relativity playlist. But for C, we end up with 3 meters per second. Why is this 3 meters per second? Well, let's see. C has to swim a little bit against the river to stay vertical from the perspective of the shore. And in the end, whatever his velocity is, his final velocity relative to the water, the river, is 5. So he's not swimming in a straight line. He's swimming in a straight line from our perspective, but from the perspective of the water, he's going sideways. He has to compensate 4 meters per second to the right, otherwise he will never be staying on this vertical line. And now you have a triangle with a 5 and a 4. And maybe some of you can already know what will be the vertical component. The vertical component will be 3 meters per second. And why is this? That's because of the Pythagorean theorem. And I made a video about it at level 20A in my special relativity playlist. But, it's A squared or C squared is A squared plus B squared. The thing that we do in high school when we have triangles. So this is it. This is You mastered it. You're done. It will be easy from now on. So moving on. So here I have again my experiment. We know that the velocity of swimmer A relative to the shore is 4 plus 5 is 9. The velocity of B when he from B is 4 minus 5 is minus 1 to the left. Velocity is a vector, right? It has direction, not just a number. So it's minus 1 to the left, which is the same as plus 1 meter per second to the right. And C, we had to do the thingy with the Pythagorean theorem, and we get the square root of 9, which is 3 meters per second. So keep breathing. You've done all the hard work, and don't be bothered about getting the 3 wrong, because even Michelson got this wrong in 1881, and he thought it was 5 meters per second. So now we are going to have a race between the two swimmers. We are going to send swimmer A home. Thank you for your services. And we are going to race B and C. So B is going to swim a distance D to the right and then return back to the finish line. And we did all the math, so you can follow that the velocity to the right will be 1 and to the left will be 9. Swimmer C has to do exactly the same thing. He has to swim up d meters and down with a velocity of 3 meters per second, right? And then we can do the calculations, and we know that C wins the race, right? It's great, C wins. Of course, we can do this for any speed of the swimmer and any speed of the river. So let's generalize and just keep the equations. Keep breathing again. It's not difficult. This is what the equation was for the swimmer B. This one was, again, we know when we wrote it down, and I put in the numbers just to have a smooth transition from actual numbers to equations, and this one was the one for C. Again, we are going to take it one step further. I'm going to replace the velocity of the swimmers with a big V, because they are the fastest. The swimmers go faster than the river, and I'm going to replace the velocity of the river with a small v, because that was slower. And that's what we will always do for the remainder of this video. Small v will be the medium, the river, and the big V will be the wave, in this case the swimmers. Let's see, so we know this one. We did this, and we can write this down like so. Michelson and Morley did, of course, but it just fell out of the sky. So I will add the mathematics in my rant video, and here you can see the actual equation from the paper in 87. This can be further approximated by this one, and again I will add the mathematics that justifies this simplification. When we look at length is just the same as the time the swimmer was in the water multiplied by its velocity, which is the big V. So if you multiply TB with the big V, we get LB, and here it is in the paper. And again, we can approximate this with this one, which is in the paper as well, and in the rant video I will show you how this is done. Moving to swimmer number C, this was the equation. We can write this down as this, doing some approximation, and this can be even further simplified into this equation. And again, I will add this in the rant. And if we look at the length of swimmer C, then again, TC times the big V gives us this equation, and there it is. And that can be simplified the same way into this. Forget about the simplifications. Forget about rewriting the equations. We will move on with the last pieces of the equations, and just accept them as they are. And if you want to know more, go to the rant video and I will show you how to do this. Because now we have all the equations, we can look at the delta t. The delta t, well, you can do this yourself in this video, I guess. Just subtract tc from tb and you will get this equation. And if we do the same for length, we get this equation. And here you see it in the paper itself. Et voila, no more math, you're done. Relax and let's move on to the next slide. We are going to have a crash course in light because that's what we need for the remainder of the video. I already put out some videos on light. Well, not some, a lot of videos, and it's difficult. It's way more complex than the stuff we're doing in this video, so I'm not going to repeat this. But if you are really curious about what is light, what is the mathematics and the physics about it, you can watch my videos in the special relativity playlist where I will build it up from the ground all the way to level 14, the Maxwell equations, and then move on to level 16. Here we are going to do it in like 30 seconds. Light is an electromagnetic wave. And if you don't know what an electromagnetic wave is, maybe you do know what Wi-Fi is, right? Your phone connects to the modem using electromagnetic waves, and these have a very specific wavelength, these waves, and that's why they are in the range of the Wi-Fi spectrum. You probably have a microwave at home. The food gets heated by electromagnetic waves. Radio using antennas, electromagnetic waves. Feeling the heat is infrared, electromagnetic waves. Getting a tan on your skin, UV light, electromagnetic. X-rays when you go to the hospital, when you broke a bone, they can send electromagnetic waves through your body and they will show your bones. And somewhere in the middle is electromagnetic waves of very specific frequencies, and apparently our eyes are very those are the sensors, and those are the electromagnetic waves we can actually see. But it's all the same. It's really all the same. They knew this already when in 1887 when Michelson and Morley were doing this. So here I have the animation. I took it from my playlist on special relativity. And you see an antenna and electrons going up and down. That's how we create radio waves, just electromagnetic waves of a specific wavelength. And you see it's actually two waves perpendicular to each other. One is changing the electric field strength along its way, and the other one is changing the magnetic field strength along its way. If you are afraid of math, then I would suggest you close your eyes and cover your ears, because I am going to show you the equations that govern electromagnetism, and it's these four equations. It's called the Maxwell equations, and if you do some mumbo jumbo on it, you will get the actual wave equations, and I did all this stuff in my playlist on special relativity. And I believe the Maxwell equations are of such great importance to mankind, because everything we do, every electronic device is built upon these four equations. So I have a picture of these equations on my wall in the house to celebrate their fame. If you do want to know all there is to know about Maxwell's equations, go to my special relativity playlist, and there you will have it all. Next, time to get serious. We are moving away from swimmers and rivers and slowly getting to the actual experiment by Michelson and Morley. The river is being replaced by the ether, and we will replace the swimmers by light rays. And instead of the shore, we have a room, and this is what the actual experiment looked like. Let me get me out of the way so you can see it in full glory, and we will dive in and discuss every single detail of that setup. Next, the genius of Michelson. So he wanted to have this race between the two light rays, just as the swimmers did, and measure the difference at the finish line. And how on earth, it's a great idea, but how are you going to uh, 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 make a device that's able to do so? And well, he managed, he built a device that could do this. And here's a picture, well, a schematic of the device from the 8081 paper. And if you run the numbers, then the difference in time between the two light rays will be 0.000000008 seconds. So you will never be able to do this with just your stopwatch. You need to find another way. So what he said was, okay, maybe we should not try to measure the delta t, but let's measure delta L, because delta L is delta T multiplied by the big V, and the big V in this case is 300 million meters per second. So maybe delta L is something we can measure. So we shifted focus from delta T to delta L. But if you then run the numbers, you get in the range of wavelengths. Ray number C, the one perpendicular to the ether, will be less than a wavelength ahead of B. So it's still difficult. And then he made another brilliant idea. And then he said, no, but maybe we can have these rays interfere on the finish line and look at the interference pattern. And later in this video, I will go deep dive on interference and how you can see this, because that was something they could do at that time. Okay, we're gonna race the two light rays. How? Well, I'm going to explain later how, but just go with the flow. It's no different than the swimmers in the river. The river is now the ether. The swimmers are now light rays. And I'm just going to open up this slide completely. And the math and it's exactly the same. You did this, just put in different numbers, put in 11 meters for the D, put in 300 million for the big V, put in 30,000 for the small v, and you will get the answer. The delta L in a single race will be 110 nanometers. If you want to express that in wavelengths, let's say the wavelength was 550 nanometers. In my rant video, I will rant a lot about the lights and the wavelength information in the papers, but for now, just go with the flow, 550, then that would be 0.2 lambda. So the difference between the two rays is 0.2 of a single wavelength. So, and that's something they could detect by looking at interference patterns. But that's not what they did now. Well, I'm not sure what they did. Again, rant video. But I guess they took a picture of this experiment and then they rotated the entire device 90 degrees. And now B wins because B is perpendicular to the ether and C is aligned. And you can do the same numbers and you will find that B wins by 0.2. And now you can combine these two experiments. So race number 1 was won by C by 0.2. Race number 2 was won by B, now perpendicular with 0.2, and together. And if you now take a picture of that second race, then the difference between race number 1 and race number 2 would be 0.4 lambda, and that's what Michelson and Morley also put in their paper. And here's how I got to the 550. They said D was around 11 meters, and that was the same as 20 million wavelengths of yellow light. Rant video, yellow light. What is yellow light? Well, in this case, 550 nanometers, and that's how I got to 0.4. 0.4 is something you can measure when we go into the interference stuff, but we're not going into the interference stuff. Now we are going to actually look in detail on the setup. It's animation time. Let's pull the curtains. Here we have it. This is the floor of Michelson and Morley in 1887. and let's put some bricks on it. Let's slap some concrete on it. And let's put this thing of metal. I don't know which metal, the article doesn't say, but it's a casing fixed to the base. And they filled this casing with liquid mercury. Can you imagine Morley and Michelson, la di da di da, and they pour liquid mercury in this casing. I don't know about the health issues back then, but okay, so that's why did they fill it with liquid mercury? Because this is a master marker. We'll get into it. They put a concrete ring that floats in the mercury, and because of the mercury and the dimensions, they were able to extremely precisely and smoothly turn this concrete ring around. And they also put 16 markers here in red on the thing, so they could always know how the ring was oriented versus the base. We're not there yet. Now we have to put another stuff on the ring. So this is fixed on the ring. So this slab can rotate. And this is the foundation for their experiment. And first we need a light. I just made an artist impression of a light here. And we need a lens to focus the light into beams. I just did something, just a round piece of glass. And this is really important. In the middle of the experiment, there's something called a beam splitter. And it does what it says. It splits a ray of light into two perpendicular rays. How? It's just a piece of glass. And on one end, they sprayed it with silver, but not fully covered. They sprayed it with a little bit silver, such that half of the light just passes through the glass, and the other half is reflected by the silver. And if you aim at 45 degrees, then you will split your beam in two half beams 90 degrees apart. These beams went to the corners of the experiment where they put a lot of mirrors, making it able to have the light rays bounce back and forth, back and forth. And the more they bounce, the longer our variable d will be. So they did not have a device with arms 11 meters long. No, it was smaller, but the light has to go bouncing between those mirrors. Let me show you. So here you see the mirrors on each corner, and just bounces to 1, back to 1, 2, 2, 3, 3, 4, 4, 4, 3, 3, 2, 2, 1, 1, and then it meets again at the beam split. So this is what happens. The compensating glass is there. I will talk about it a little bit later. This is an important thing. This is where both light rays in the end, this is the finish line. They will get to the interferometer. And this is where Michelson and Morley were looking through, watching the interference pattern. So let me break it down again. There is a piece of light here for demonstration purposes. I cut a piece. It's colored red. It's not red light. They used sodium light, they used white light, but just to make it pop off the paper. It's red here, and it hits the beam splitter. The beam splitter, half of it goes through. I marked it blue. No, the light does not change color. It's still the white light or the sodium light, but again, for demonstration purposes, blue goes through, and the other half is being reflected by the silver, which is green. Then they go to their mirrors, they bounce back and forth, they will come back to the beam splitter. Now green, half of green can go through, half of blue is being reflected by the silver, and those together are interfering with each other, and that goes into the interferometer. Maybe I should just show you something that moves, right? Here we go. I think this is it. Yeah, here it is. So watch the ether. The camera is just spinning around the setup. The setup is not moving at the moment. Blue is swimmer B, and green is swimmer C, perpendicular. And watch. We are going to recombine. Not yet, not yet. No. Now I think. Yes, Did you see it? Did you see the red ones combining? And now you can look at the interference pattern. Let's talk a little bit about the compensating glass. What is this? It's just an ordinary piece of glass with the same thickness as the beam splitter. And why did they have to do so? Here's schematics from the original paper. And here's our beam splitter. Red is the silver layer. If we look at the beam that gets reflected first by the silver, it goes into the glass. Whenever light, switches medium, it bends a little bit. It gets reflected by the silver back to the glass, from the glass through the air, hits the red mirror, comes back at number 5, goes again through the glass at 6, and now half of that light in 6 is passed as number 7. And you see that this beam, number 7, all the photons in this light ray went through glass 3 times. Okay. Now let's look at ray number 2, which is swimmer number C. It comes in, goes into the glass, number 1, half of it goes through, goes into the compensating glass, 2, hits the mirror, comes back, goes through the glass again, 3 times glass, then hits the silver, and half of that light is being reflected into number 9. So also this ray went through glass 3 times, and that made it a fair race because light changes velocity when you go through different media. So this race was not rigged, and now we can compare what happened at the finish line. Moving on, 3 times. So this is what we know. I'm not going to repeat this again. We have delta L, the difference between the 2 light rays in a single race, and we have delta delta L, the difference between 2 races which are 90 degrees apart. And how can we measure these? And well, we can measure these by looking at interference. So our next topic will be interference. What I did is I built an online interference simulator, and you can just go there. Everyone can use this. The URL is in the page, and I'm going to take you there right now. And here we see a single wave, and let's animate it by pressing play on the time button. And let's say this is the ray of light for swimmer B, the one that's behind, that loses the first race. Let me pause it a bit, and then I have another one, and this is C, the one that will win the race. And this one is also, just moving through space. But if you combine them, well, you can't see the combination because they are perfectly aligned, or not only aligned, but they are exactly at the same time at the finish. So let me say that 0.2, yeah, you wanted to go to 0.2. Let's make sure that, well, 0.1, 0.2, I got 0.2. So here you see that C, the purple one, is just 0.2 wavelength in front of B, which is the red one. And if you would look at the interference pattern, you would look from this side. And well, this is not really what we want to see, because if we add these together, I have this one as well here, that's the green one. The green one is the interfered wave. So you never see this one, you never see this one, you will only see this one. So you will just see light coming into your interferometer. And based on the displacement, that light will, why is it turning? Don't turn. Huh. Based on the displacement, the light goes down. This is where they can cancel each other out. Let me see. If C is right, exactly 1/2 wavelength in front of the other, if you add them together, then you will get this cancelling out. So this is not really what we want to use. We want to use something else. Let me stop time for now, and let's bring back the, well, let's put the misalignment, not the misalignment, let's say that the difference, 0.2. C wins by 0.2. But I don't want this green thingy here. I want something else. And how can you do this? You can, if we go to the top view, I can misalign ray number C a little bit with B, the red one. And now if you look at the resulting wave, let me get the original waves out of the way, we see something like this. And the more the misalignment, the more we see this. And this is great because now if you look into the, well, let's put on the animation again. If you now, and this is sideways, but if you now look to the front of the light, you will see these fringes. You know, they will actually look like vertical fringes on the screen in the interferometer. And the other thing is, if there's a change in the delta L between the two rays, these fringes shift. Do you see them shift? I mean, even if they are at the same time at the finish line, we still see these fringes, right? And if one is one full wavelength ahead, you see the fringes shift also one position. And that's the magic. Because you can see these fringes, and if you see one of those fringes move to the next location, you know that delta L will be 1 lambda, 1 wavelength. We were looking for 0.2 lambda or maybe 0.4 lambda, so something around the change between this, between 0 and 0.4. It's a bit like this. This was the movement they were looking for, and that's how they did it. Brilliant, isn't it? Let's go back to the slides. Where are we? So what I did is, you know, these are two aligned wavelengths, and if you add them up, you just get, well, another wave. But if you misalign them, you get this much more interesting pattern, resulting in fringes. This is how the fringes would look like if you used a sodium light. But, you know, if you are looking for very small shifts, it's difficult to use this yellow light because if you blink with your eye, you don't know which fringe was which fringe. So that's why they switched to white light. White light has a little bit of difficulty because white light is not a single frequency. You know, it has a range of frequencies. But in the middle, there is this black line. And if you just keep your eye on the ball, on the black one, you can see the shifting going left to right. So the displacement of one wavelength, delta L, is the same as the shift of one fringe. And that's how they did it. I mean, it's just amazing. It's really, really brilliant to see how they did this. So final conclusion. We are at the end of this praise video. This is the results. And what you see here is the black lines are the measured fringe shifts as a fraction of lambda. They were, and they did this at noon and they did it in the evening, PM. The dotted line is what they expected to measure. But the dotted lines are here a little bit misleading because the actual dotted lines need to be 8 times bigger. So imagine the dotted lines being 8 times bigger, that's what they expected, and see what they measured. The measurements were way, way too small. They didn't even come close to what the theory had predicted. Here you can see, you know, here the theoretical maximum is at 0.05 lambda, but that's the same as the 0.4 that we were looking for divided by 8. So it was nowhere near 0.4, and that's what they said you saw. The actual displacement was certainly less than the 20th part of this and probably less than the 40th part. So that's well within the range of measurement errors. No displacement, no ether, or maybe the ether was just at rest, because then both light rays, if it's at rest, then it doesn't matter. It's like the river is not flowing, then B and C will have an equal race. Maybe that's what happened. Maybe they should have looked at also the sun and the solar system is turning, what is the ether, what is its frame of reference, right? Maybe we should do it on the top of the mountain. That's what something they suggested. They also said, maybe we should be more careful, because if mirrors are moving and you bounce light on it, then it's a little bit tricky, a little bit different. Maybe that's what's going on. Maybe it was the wrong time of year and we should repeat. So they were looking for alternative things, but the final conclusion is you don't need ether. You don't need an ether theory to explain all the physical phenomena in light. You can do this with other models that came later, and also special relativity rules out the need for ether. So you could say it was failed, but I would say, it did not fail. You learned something about actual physics. So what did I not do in this lengthy video? I did not go deep dive on the preamble, how did we get to this experiment. If you want to know a little bit more, you can go online and look for these things. There's a supplement in the article which talks about light bouncing off moving mirrors. I did not do that. I can say, there are many follow-up experiments, and they proved the outcome time and time again with much more accuracy. The result is always the same. Light will always meet in the end at exactly the same time. No one wins the race. No ether theory. Don't forget, this was my praise video, but boy, oh boy, oh boy, am I going to rant. See you there. Bye bye.